Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing the metal carbonyls and related compounds. In that case, we have seen the introduction and history of metal carbonyls, and now we are going to see the next point of this topic, that is characteristic features of metal carbonyls. So in this case, we have to see how these metal carbonyls form and what are the basis of the formation of these metal carbonyls and what are its applications. What are the basis for the applications? Now the first effect, this characteristic feature, is that D block elements So these D block elements, we know that they are having the N-S orbital, then N-1 D orbital and N-P orbital. So in this way, we have to, means metal can use there, or in short we can say, if we are considering these N D orbital, the D orbital is shown as ND, then it will have the N plus 1 S and N plus 1 P orbital. So with the help of this, and depending upon the number of electrons present in this ND, their behavior of these D block elements is considered. We should know that the D block elements have their positive oxidation states ranging from 1 to 7, like that, or in some cases they are also more. But the metal ions or metals are having oxidation states such as low oxidation states may be 0 or less than that, that is -1, like that, means low negative oxidation states are also possible. So the metal ions have ability to form complexes with neutral molecules. First is, they can form complexes with neutral molecules, such as carbon monoxide, nitric oxide, similarly CMI or RCN, you will say, then pyridine, then bipyridine, then PHE and phenantholene, I-, Br-, etc. So negative ions are also used for the formation of complexes. In many of these complexes, the metal ion, as we have just seen, that the metal ion can exist in low oxidation state, means in order to form complexes with neutral ligands, the ligands should have, means metal should have low oxidation state, 0 oxidation state, or even low negative oxidation states, because the metal ion can be stabilized in their low oxidation states by the neutral molecules like carbon monoxide, etc. In this case, the neutral molecules like carbon monoxide, means carbon, nitrogen, etc., are having vacant orbitals, vacant p orbitals of pi nature, and they can share the electrons donated by metal ion. So this is necessary in order to stabilize the molecule because during the formation of a metal complex, the ligand first of all donates its lone pair. So lone pair of ligand is shared with metal ions, and this produces sigma bond. But as a result of this, the ligand becomes positively charged, metal ion becomes negatively charged, and this charge separation is unfavorable to stabilize the complex. As a result of this metal ion has pi electrons of pi nature, or electrons present in the orbitals of metal ion, d orbitals of pi nature. So these d pi electrons are shared with the vacant p orbitals of ligand which are of pi nature. So this gives pi bond. So here two types of bonding is observed. First, ligand to metal, it gives sigma bond. This is sigma bond. And another is, so here the ligands utilize the p orbitals of sigma nature, and here d orbitals of sigma nature. But in case of the metal to ligand bonding, the metal has pi orbitals of d nature and pi orbitals of p nature, so which produces pi bonding. So here we have to remember that the formation of sigma bond shows unfavorable charge separation on metals and ligands. And in order to remove this unfavorable charge separation, this metal ion, which is electronegative, is forced to share its electrons or give back their electrons to ligand. For this purpose, the d orbitals of metal ion of pi nature, that is filled orbitals, are overlapping with the vacant p orbitals of pi nature of ligand and gives the pi bonding. So formation of sigma bond favors the formation of pi bond, and formation of pi bond strengthens back this sigma bond. So this is called a synergic effect. Synergic effect means sigma bond is favoring the formation of pi bond, and formation of pi bond strengthens the sigma bond. So this is called a synergic interaction. Therefore, such type of metal carbon bond formation of sigma and pi nature stabilizes the metal complex, that is the metal carbon bond of the neutral species is strengthened due to the formation of first sigma bond followed by the pi bond. So for this purpose, the metal ion is, what is the requirement? Metal ion should be in low oxidation state, low positive oxidation state, or zero oxidation state, or low negative oxidation state. This is the essential requirement. Metal carbonyls are used as precursors in organic synthesis or synthesis of organometallics. The bonding of carbon monoxide to the metal is highly sensitive and shows electronic effects, and as a result of this the formation of a metal ligand bond is monitored by IR spectroscopy. Then another feature of this transition metals is that these metal carbonyls exist in atomic state, means as a monomer or mononuclear complex, dinuclear complex, trinuclear means polynuclear complexes, and we will see some of the examples. For example, NiCO4, then FeCO5. So these are examples, or we can have also CrCO6. So these are the simple. Then binuclear, that is Mn2CO10. Then CO2, CO8. Then trinuclear, osmium, CO12. Then IR4, CO12. So these are a few examples of polynuclear metal carbonyls. So we are showing that these are mononuclear and these are polynuclear metal carbonyls. So we can show some structures of these metal carbonyls. For example, first we will see the structure of this metal carbonyl Mn2. So this Mn, the two Mns are bonded by this way, a sigma bond. In addition to this, they will have the bonding with carbon monoxide in this way. This is Mn2CO10. Mn2CO10. Now another structure can be shown like this. CO2. So we have seen this structure. Now this CO2, CO8. So carbon, cobalt bonding is like this. Then there is bridge bonding, like this, and this terminal. So this is CO2, this CO, carbon, cobalt 2, and carbon monoxide molecules, these ligands are 8. Now another structure we can see here is like this. For osmium molecule, OS. like this. So this is osmium carbonyl complex, and now again we will see the last this IR4. So this shows the bonding between the IR metals, and carbon monoxides are 12. So 3 carbon monoxide per IR. Like this. So in this way we can have IR4CO12 complex. Now in all this complex formation, the important thing is that every metal shares their valence electrons. Every metal shares valence electrons. Every ligand shares 2 electrons. 2 electrons per ligand. And if we count these numbers, it becomes equal to the number of electrons. Number of electrons equal to next noble gas element. That is inert gas configuration of the next noble gas. So this is called a noble gas formalism. This is called a noble gas formalism. Means the formation of metal complexes results in the electronic configuration of central metal ion and electrons surrounding it. Shows that the total electrons are becoming equal to the electrons present in the next noble gas or inert gas. Here we have seen that every metal makes use of its d block, that is Nd orbitals, then n plus 1 s orbital and n plus 1 p orbitals. So this formation of complex involves such type of orbitals. Ligand contributes the p or d orbitals for sigma bonding, p or d orbitals for pi bonding. So in this way the strength is strength of metal ligand bond on carbon metal carbonyl is increased. So this is of considerable utility in the designing variety of complexes, that is metal carbonyls, nitrosids, isocyanates and their substituted products. So this rule is found to be observed commonly, but still there are some exceptions in which the noble gas configuration is not attained. We can take the example of vanadium CO6, VCO6, that is vanadium CO6. And another example is Another example is this Mn CO2 diphos two plus 1. And here this diphos is nothing but the 1,2 bis diphos P diphos phosphino ethane ethane. So these carbonyl complexes are of structural importance. Similarly, they are having industrial importance and catalytic importance also. They are also important in variety of reactions. Their composition is governed by the tendency to form closed electronic shells. So metal carbonyl variety of applications in this way, with the formation of one of that application is formation of metal carbonyls and related compounds such as nitroses, hydrides, or these halides, etc. So we will stop our discussion here and we will go to the next point in the next lecture. And if not yet, please subscribe to this channel so that the information of new episode or video will be brought to you immediately. Please press the like button. So thank you very much. See you again.